In this tutorial, we'll explore the Kubeflow open source framework for machine learning pipelines. What makes Kubeflow particularly powerful is that it allows you to focus on building your machine learning pipelines without getting caught up in the technical details of how they're implemented. For example, if you're using Google Cloud, you can run your Kubeflow pipeline specifications through the Vertex AI pipeline service with minimal setup. Similarly, if you're working with Amazon Web Services or AWS, you can run these same pipelines using AWS SageMaker in a managed way. Today, we'll focus on concepts that work across different cloud platforms rather than focusing specifically on Google's Vertex AI pipeline service. To begin our journey, we'll use a Jupyter notebook on Vertex AI Workbench, which is part of the Vertex AI suite. This tool makes it easy to create pipeline specifications and run them using the Vertex AI pipeline service. We'll start with a new project in Google Cloud. First, we need to visit the Vertex AI homepage and enable all the recommended APIs. After that, we'll go to the Workbench section of Vertex AI to create a new instance. While the default settings work well, you might want to choose a smaller machine type to reduce the hourly cost from 20 cents. For this tutorial, we'll proceed with the default settings. After our instance is ready, we'll open it in our browser. This is where we'll write and run our Kubeflow pipelines code. Let's create a new notebook using the Python 3 kernel. We'll give it a descriptive name and then install several important packages using pip. These include the Google Cloud AI Platform Library, Kubeflow pipelines, Google Cloud Pipeline components, and we might add some visualization libraries later. Even though Python isn't typically known as a typed language, we'll use type annotations in our code. Our imports will include Kubeflow pipelines code for handling components, pipelines, and various artifacts, as well as Google Cloud Vertex AI libraries that help us work smoothly with the Vertex AI system. It's important to note that there are two versions of the client SDK, version 1 and version 2. In this tutorial, we'll use the version 2 client SDK and work with the AI platform import to manage our pipeline job specification. We may also use some pre-built Google Cloud components in our pipeline, but let's hold off on that for now. Next, we need to set up a Google Cloud storage bucket to store various elements of our pipeline. We'll use the gsutil command to create this bucket. Initially, we try naming it Vertex AI Pipelines Demo, but since that name is already taken, we'll need to try a different name. Once we successfully create the bucket, we'll configure several important settings: the region where everything will run, and the pipeline root directory, which will store our logs and artifacts. We'll use our newly created bucket for these purposes. Now comes an exciting part, creating our first pipeline. Think of this as a Hello World example for Kubeflow pipelines. We're keeping things simple and not diving into complex machine learning concepts yet. Our pipeline will consist of components, which are the basic building blocks. These components will use Python's user-defined functions and will use a special decorator from Kubeflow's DSL or domain-specific language module to turn these functions into pipeline components. For our first component, we'll create something very basic, a Python component that takes a product name as input and simply returns it. This component demonstrates the fundamental concept of inputs and outputs in Kubeflow pipelines. When we compile this component, it creates a YAML file. This YAML file looks similar to a Kubernetes resource file and defines what our component does. By defining it in YAML format, we make the component reusable in other pipelines. Let's create a second component to explore more advanced concepts. This one will use the same base image as our first component, but we'll add a packages to install argument. This feature allows us to include external libraries in our component. We'll use the emoji library as an example. This component will take an emoji name as input and return two pieces of information, the emoji text and the emoji itself, both as strings. It's important to note that we don't need to install the library in our notebook. It only needs to be installed when the component runs, since each component operates in its own Docker container with its own environment. When we try to compile this second component, we encounter an issue with the named tuple output format. To simplify things, we create a custom class called emoji output that has two attributes, emoji text and emoji. This makes our second component ready to use. After we successfully create our third component, we're ready to put everything together in a pipeline definition. Similar to our components, we use a decorator from Kubeflow's DSL module. We give our pipeline a name and specify its running location in terms of the Google Cloud Storage bucket. The pipeline includes inputs that can be set each time it runs. For each input, we provide a type and optionally a default value. One of the most powerful features we implement here is using the outputs from one task as inputs to another, effectively linking our components together in a workflow. With our pipeline configured, we're ready to run it. We first initialize our AI platform library and prepare to submit the job. An important step we shouldn't forget is compiling the pipeline into its JSON format before running everything. Once we have our pipeline job specification in JSON, we can submit it using the AI platform's pipeline job function. When we check the Google Cloud Console to see our pipeline in action, we can observe how our tasks are automatically connected. However, we encounter our first challenge. The pipeline run fails because our compute storage account lacks sufficient permissions for the bucket we set up. To fix this, we navigate to the bucket's permissions and grant our service account cloud storage admin permissions. One convenient feature of the system is that we can easily clone and rerun the failed pipeline without any additional setup. While we could modify the default inputs at this point, we decide to run it as is to see if our permission fix resolves the issue. The second attempt shows improvement. Our components start running. We can see the inputs flowing to our tasks, which will eventually feed into the final build sentence component. However, we hit another snag when we encounter an error related to the emoji output class. To resolve this, we try simplifying our approach by using Python's tuple library in our emoji component instead. When this doesn't fully solve our problem, we make a third attempt using a dictionary structure instead. This leads to an interesting discovery. When we rebuild and rerun the pipeline, we notice that tasks which ran successfully in previous attempts are being cached. This caching feature means we don't need to rerun unchanged components with the same inputs, saving both time and resources. While this caching behavior can be overridden if your tasks aren't deterministic, it's a valuable feature for optimizing pipeline execution. As we debug our pipeline, we notice we forgot to update a variable name, so we recompile and run the entire pipeline again. Finally, we achieve success. All our variable names are correct in the emoji function, and we can see the output producing the expected emoji based on our text input. We now wait for the final output from our last task. This task demonstrates an important concept in pipeline execution. It cannot begin until it receives outputs from both parallel components we started earlier. This showcases how Kubeflow manages dependencies between pipeline stages. Our final successful run combines our text and emoji as intended, completing our Hello World example of a Kubeflow pipeline. Throughout this tutorial, we've learned several key components: how to create individual components, how to install additional packages within components, how to link components together in a pipeline, how to handle permissions, and how to deal with pipeline caching. We've also seen how to troubleshoot common issues that might arise when building pipelines. The example we've built, while simple, demonstrates the fundamental concepts of Kubeflow pipelines. We've seen how to create reusable components, connect them together, and run them in a managed environment. We've also experienced common debugging scenarios and learned how to resolve them, from permission issues to variable naming problems. This serves as a foundation for building more complex machine learning pipelines. Whether you're using Google Cloud's Vertex AI, AWS SageMaker, or another platform, these concepts remain consistent. The ability to create modular, reusable components and connect them in flexible ways makes Kubeflow a powerful tool for machine learning workflows. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include all the code and diagram files in the description as well. Thank you very much for watching to the end, and please enjoy responsibly.